So I'm going to talk about something quite elementary that I first encountered here in Bonn, more or less at the time of the workshop, because I was doing my PhD thesis here, and I never ever spoke about this topic. I think it's quite beautiful. So conical sums are certain numbers, certain periods, which generalize multiple zeta values. They're also known as conical zeta values. And I encountered them in my PhD thesis, and there were some conjectures back then, and I was hoping to attack these conjectures soon, and then finally, 6 years later, I had some time to attack the conjectures with Eric Panzer in Oxford. Unfortunately, this is still a work in progress. When I proposed this topic for this workshop, I was very optimistic. But I'm gonna tell you what's the current state of the art, and it's also nice to finally have a talk on this topic that I really liked. It's gonna be very elementary, so I apologize if you get bored about elementary things. Okay. So to understand how elementary this may be, the first slide is really going to be super elementary. So this is an example. So you have zeta 3 that you all know, and you probably also all know that can be written as this double sum. This is also called zeta of 1, 2. And this is by what people call extended double shuffle relations. Then there is this change of variables that you can do to rewrite it like this. And I do this because later on you will encounter generalizations of this kind of series. And of course you can do partial fractioning inside of the sum, and you immediately find that it can be rewritten this way. And then you can do something a little bit more complicated, and you can rewrite it in this way. So this quality is already not completely trivial. And then again, you can do the same kind of thing that you did here, so you can do a change of variables, and you can rewrite it as this sum. And I think when you get here, you completely lost track of the fact that this is zeta 3. So this is to start introducing the kind of numbers, the kind of series of several variables that I'm going to talk about today. So this is a prototype of this kind of sums, and I'm calling them conical sums because here you're summing over lattice points inside some cone in R2. Okay, so later we'll see the definition, but first I want to talk a little bit about multiple zeta values. So some of you are experts on multiple zeta values, but I want to recall some things and maybe introduce them from a slightly different viewpoint that is going to be easier than to generalize to these conical sums. And I apologize for the slide talks, which maybe some of you will not appreciate very much, but I have many formulas and I thought it was just easier. I'm happy to give you the slides if you are not able to take all of the notes in time. I think it's also recorded, so you can take a look at that. Okay, so multiple zeta values. Multiple zeta values are defined as this nested series that converge only if you put this condition kn bigger or equal than 2. They have some depth n and weight, which is the sum of these entries k1, kn. And they were first, in the very easiest setting, they were first considered already by Euler, who studied special values of the Riemann zetas and also took a look at the n equal 2 case, which are double zeta values. Then I think they were rediscovered and systematically studied starting from the end of the 80s, beginning of the 90s, by people like Don and Hoffman and many others. Okay, so today it's quite important to take a look at this kind of picture. So you have the product of two multiple zeta values, like very easy ones, zeta 2 times zeta 2 is equal to this series in two variables. And you can see this as a sum over lattice points inside the first quadrant of R2. And you can split this, so you can take the sum over the points which lie above this line, the points which lie below, and the points which are precisely on the line. This is what you're doing here. And that's one way to find some relations between in the algebra generated by multiple zeta values. Because here now, this you recognize is equal to zeta of 2, 2. This is also equal to zeta 2, 2, and this is equal to zeta of 4. So you find this relation, which is called the quasi-shuffle or Stafford relation. And here you already see some cones, so that's what I want to generalize later. Multiple zeta values form a very nice vector space, which turns out to be an algebra because of this kind of quasi-shuffle relations, which is filtered by the depth of multiple zeta values, but you can also have relations between multiple zeta values of different depth, as we have seen in the first slide. So that is going to be just a filtration on the space, but then you can also introduce the Q vector space spanned by weight k multiple zeta values, whose dimension is denoted dk. And after numerical experiments, Zaghe conjectured that, this is a grid algebra. So this is a direct sum decomposition of the weight k spaces. And there is a formula which is conjectured to be this one for the dimensions. So now we know that this gives numbers which are an upper bound for the actual dimensions, but we still need to prove that it's a lower bound, and this seems quite hopeless. Because it's difficult to prove that numbers, transcendental numbers, are actually transcendental and independent. So, just an example, here you have d0 equal 1 because it's just q, d1 equals 0 because there are no weight 1 multiple zeta values, then weight 2 there's only zeta 2, but this formula then tells you already what are d3 and d4, but d3 is the dimension of the space generated by these two guys, so this tells you that these two guys must be linearly dependent, and that's the relation that we've seen in the first slide. And d4 equal 1 tells you that these numbers have to be all multiples of zeta 4, which is true, but you need to work a little bit to prove this. So there are many relations among multiple zeta values, because the space of all multiple zeta values of weight k goes like 2 to the k minus 2, something like that. Good. So Stafford relations, quasi-shuffle relations don't suffice to describe all the relations, so there are also shuffle relations. I'm going to be very fast on this slide because you probably all know shuffle relations, but also if you don't know them, this is not really the approach I want to look at today. But anyway, so multiple zeta values have an integral representation. Well, they have many integral representations, but this is one that was, I think, first maybe proposed by Konsevich. This already tells you that multiple zeta values are periods, by the way, which is the topic of the workshop. And if you now take products of multiple zeta values using the integral representation, then you can do, you have a domain like that for your integration, and then you can shuffle these variables, and that's why they're called shuffle relations. You take all the possible combinations which still respect these constraints, and you get this new relation, which is different from the previous one, because essentially because this guy and this guy are, sorry, well, I can't do it in my head now, but 2 of these 6 give a zeta 2, 2, and the other 4 give zeta 1.
So it's
Should there be a plus
yeah.
instead of equal?
Plus.
On the second left.
Yeah, it's a plus.
Yeah, that's a plus, thank you, sorry. But then you put together these two kind of relation, and you raise then the zeta 2 to the square, and you find what are called double shuffle relations, which is in this case just 4 zeta 1, 3 equals zeta 4. So this is now a linear relation between multiple zeta values, right? Whereas these were just in the algebra generated by the multiple zeta values. But that's not the approach I want to use for shuffle relations. What I would prefer is to have this kind of integral representations for multiple zeta values. Well, this is just trivial to pass from this representation to the other. You just do a change of variable, the exponential can be transformed into just variable I, and then you get an integral over 0, 1, and then you can do another change of variables to have simple. But now you have this cone, 0, infinity. You have the whole first quadrant. And then you can do the decomposition of this cone in this way. And well, you do this, you get two integrals, but then you do again a change of variables here, which is this change of variable. And you get these two integrals over 0 infinity square, which can, by the same trick that was applied here, be written in this way. So now you can just sum over x1, x2, and you get the same shuffle relation that I wrote down before. And if you are, and you can immediately also see that you could have already guessed this relation by just doing some partial fraction decomposition. But I like to present this as a decomposition of cones because of the title of the talk. Okay, so so this is how I want to think about shuffle relations. And
that's the two-variable case. Yeah?
That's a two.
I mean, you may have some canonical change of variable. For three variables?
No, you can do this for any number of variables.
There is always a canonical change.
Yes. So in fact, there is also for even more general objects and multiple zeta values, you have this kind of change of values. I'll get to that later. Okay, so now let me do a brief summary of multiple zeta value algebra, shuffle, quasi-shuffle relations. So you have two series representations for multiple zeta values. So you have the usual one, and then you can do an easy change of variables to get this series representation. Then you also have two integral representations, which are this one, and you pass from one to the other via change of variables. Of course, here I'm not telling you in general what is pk and qk. It can be worked out quite easily. What I would like you to notice is that in the integral, here you have an easy domain and a complicated integral. Well, complicated, not quite, but not completely, not as easy as this one. So the complication here is in the integral, but the domain is easy, and also qk is easy. I haven't written down, but it's easy. Whereas here you have a canonical integral, which is going to be the same for all multiple zeta values. And the complication goes into the integration domain and into this pk polynomial. And the same goes with the sum. So you have a complicated domain and easy summand, and complicated summand and easy domain. This is going to be generalized later. And then how to think of shuffle relations now with this picture. So shuffle relations can be seen as the composition of closed cones in the first integral representation. So this is, well, not quite, we have just seen a very trivial example, but in general you can generalize that example and claim something like that. And this is equivalent to doing partial fraction decomposition on the summand in the second representation. So cone here and summand here. And quasi-shuffle relations can be seen as the composition of open cones in first series representation here. So the open cones, because in the summand you also have to count the lattice points on the line, whereas in the integral you don't have to. So it's a closed cone, and here they are open cones. That is going to be the terminology later. And this is not very well known, but it was, I think, first noticed by Racinet, or maybe by somebody earlier, but I've seen it in the thesis of Racinet, that quasi-shuffle relations correspond to partial fraction decompositions in the integrand of the second integral representation. So there is this kind of duality between sum and series and shuffle and quasi-shuffle. And this completely generalizes to these more general objects that I'm going to talk about. Do you have any questions about this?
When was Racinet's thesis?
Sorry?
What year was Racinet's thesis?
2006 or 7?
Okay.
Or maybe earlier. Okay, sorry. Okay, so the conjecture, very well-known conjecture, is that all linear relations among multiple zeta values are extended double shuffle relations. So it means you combine shuffle and quasi-shuffle to get linear relations, but then this is not quite enough, so you have to extend them by regularizing divergent multiple zeta values in some way. So, I'm not going to talk about this today. Good. So now I want to generalize multiple zeta values, and we're going to get to conical sums, but quite slowly. I want to show you first some examples that you encounter in nature that goes in the direction of conical sums. So the first one is not quite a generalization. It's just another kind of sum, which were considered in the past. It's not very interesting because they're all actually multiple zeta values, and it can be proven quite easily by just partial fraction decomposition in the summand. So shuffle kind of relations. But this then can be further generalized to this kind of sums. So now I'm considering linear forms in the denominator with coefficients which are just either zeros or ones. So both multiple zeta values and these model Thornheim sums are examples of this kind of series. And this is the kind of series that I encountered in my PhD thesis. And as I say here, they come from physics and geometry, because those are the two places where I've seen this kind of series. Probably they can also be found somewhere else. So I've seen them from a paper of Green, Russo, and Van Hove in the computation of perturbative superstring amplitudes. And that's also related to my PhD thesis. And then I was talking to Zorich, who told me that he encountered the same kind of sums in the computation of mathbb volumes of strata of abelian differentials. So if you compute volumes of moduli spaces of abelian differentials, I think you're just going to get powers of pi, but then there are natural ways to split this computation, and the volumes that you find are going to be series of this kind, certain specific series of this kind, and there is a conjecture by Zorich and Müller and Delacroix, who conjectured that the sums like this that they found in this context are actually multiple zeta values. This was also the question in perturbative superstring amplitudes, like, can you reduce this kind of sums to multiple zeta values? And the answer is, unfortunately, no. In general, you cannot. I will show you at some point in this talk, I don't remember when, a counterexample which tells you that in general a sum like this is not going to be in the ring of multiple zeta values.
You mean experimentally or provably?
No, I think it's provably, because it uses the data mine constructed out of shuffle and stuff.
In the other direction.
I didn't think there was any real number.
Oh well, sorry. No, sorry. What I mean is not okay. So what I mean is not a numerical thing, but it's based on known relations that it should be lying in some ring which is supposed not to be contained.
So conjecture.
Yeah, it's conjectural, but it's not numerical. Okay, but then what kind of numbers do you get? As we will see later, the kind of numbers you want to talk about, if you look at these kind of sums, are cyclotomic multiple zeta values. So you just consider, well, you can add complex variables here, z1 up to zn, and you would get what are called multiple polylogarithms, which are functions of several complex variables defined by this series. And if you restrict to roots of unity, then this is what you call cyclotomic MZVs. If the root is if these are just one, then you just get the multiple zeta values. But in general, you get numbers which conjecturally are not multiple zeta values.
Well, if you prefer to stay in some sense over Q, you could also drop the CIs and put congruence conditions, right, on the VIs. It's equivalent.
Drop the C. Yes.
If all of the CIs are roots of unity, you just put congruence as well.
Absolutely. But if you do that, and you're not going to get the complex. You're just going to get real numbers. You get just a subspace.
Well, no, but that would be a Q basis, and then you tensor Q.
Yeah, exactly. Okay, so now more generalizations on multiple zeta values. So I think these were called Witten zeta values in a paper of Don in the 90s. So Witten looked at complex semisimple algebras and considered this kind of series. And so they are called Witten zeta values. They depend on one integer k, which should be bigger or equal than 1 or 2, I don't remember. Probably 2. And the motivation was to compute some volume of moduli spaces of certain vector bundles over curves. This was motivation coming from physics, from Berlin's formula. And because of that, he introduced this sum because for physics motivation, this should be precisely the kind of sums that compute these volumes. And then how to write this sum in a way which is more similar to what we have done so far. You have to use the dimension formula. You write down what are the positive roots, and you do a little bit of you do a little bit of representation theory, and you write down sums which they will all look like this. So now I just wrote down an example with an SO5. So you see this formula looks very much like the previous ones, but here you have a 2 now. You don't just have zeros and ones. And
6 is not root of unity.
yeah, that's just a coefficient that I will want to take out. So here this is just a constant.
Yeah.
So here the k is always the same, so that's the important thing, and that's why these numbers turn out to be quite easy. I don't know if Witten actually proved this, so it was just a conjecture in his paper, and then there is a proof by Zagier and one by Garufalidis. And the statement is that if n is the number of positive roots, then this is just a rational multiple of the power of pi. Okay, but then
if k is even, maybe you said it.
if k is even, yes. I'm sorry.
It's very important. I mean,
I'm sorry.
it's not true if k is odd.
Yeah, absolutely. If k is even. And then people looked at generalization of this kind of series. So I guess this was the observation in the beginning of the paper in the 2000s. So you just consider simply algebras because you have this easy to prove formula, and then this corresponds to irreducible root systems, and then they associate. So also this one can be just read off the root system of the algebra, and then you just associate different exponents here, different powers of k to the different roots. So you write down your favorite irreducible root system. R is going to be equal to the cardinality, to the number of positive roots. And you called R zeta value, or zeta value of the root system R, something which I'm not going to define, but it's just going to be defined in the way you would think. So you have your positive roots, you have the fundamental ones, which are just x1, x2, and the others, which are going to be linear combinations of the fundamental roots. And each of those will have some power k r. And by the dimension formula, this is going to be proportional to the Witten zeta function, Witten zeta value of the Lie algebra associated with the root system. And this proportional factor here is just going to be the 6 to the k. Good. So this is the kind of more general objects that some people mostly in Japan and in China have been studying in the last 20 years.
But the original property is only for this symmetrized version, right?
This property.
That's if you have splits of reducible algebra, then you can write as a product of this. It would not be the case of this multiple
Yeah. So this is each k is the same.
Yes.
Yeah, absolutely. Yeah.
But it's still possible to consider such ones for reducible Lie algebras as well.
It is possible. Yeah. Yeah. I'm just focusing on the irreducibles. Yeah. So the example here is the root system associated with the banking diagram B2, which is what corresponds to SO5.
What is the statement? You're just saying you take the formula which we already knew, like that, and then you just change the numbers to independent numbers.
Exactly.
And so there's no theorem.
There's no theorem. There are theorems, but
sure,
I'm not going to
just...
talk about the theorem. I'm just introducing the objects that people have been looking at. Some objects that people have been looking at, the generalized ones.
You say take the thing above and just make the...
Yeah, absolutely. So there will be some theorem about some of these guys in the end of the book. Okay, so let's talk about conical sums now. So now I want to take full rank n times n matrix with entries which are non-negative integers. So these generalize this kind of numbers that we have seen, which add only zeros and ones as entries. And I define a conical sum as this series. So this may not be convergent. I'm just calling conical sums the ones for which this kind of series is absolutely convergent. And I want to assign a name to n, I call it the depth, and the weight, because they behave very much like those of multiple zeta values. But to have such, so you can do things which are much more general. It's not even clear why I call this conical sum. So one more general thing you could do is you take an open cone in R to the n, in the positive R to the n, and some m which is in general bigger or equal than n. You consider a full rank m times n matrix, again with entries which are negative. And you consider the sum over the intersection of this cone with the lattice points. So this is a more general looking kind of series, but it can be proven that it can be reduced to a few linear combinations of objects of this kind.
Do you want to intersect with z to the n or n to the n?
It doesn't matter because it's...
it's in the positive always, okay.
So, okay, so this is a fact. It can be proven. I don't think it's proven in the literature. So this is one of the things which is contained. Maybe it's not. It's not very difficult to prove this fact. And maybe it will be contained in our article. So you can do more general things here. You can take just so you can do more general kinds of coefficients. You can add a constant in each of these forms. So you can take a fine point. You can take the cone doesn't have to be contained here. You just want the forms to be positive inside of the cone, so the coefficients can be. So you can do all kinds of things. M doesn't have to be bigger or equal than n. It can be also smaller. This doesn't have to be full rank. But all these kind of things kind of gets too general, and in the end of the day, the only objects that are interesting are these ones. You can always reduce to this kind of objects. So yes, so take my word, these guys are conical sums are interesting, and all the rest of things you can think of to generalize this definition will just fall into this kind of setting.
Does the cone have to be a rational cone?
Yes, sorry. The cone has to be a rational cone, absolutely. Thank you very much.
Why the name conical?
Why
the name conical?
That's a name that was introduced in the literature. I didn't change the name.
Someone wanted to make a joke.
I mean, the conical is for the cone, right?
But the thing on the top is usually called Shintani, is that a function? Is that the name, right?
Yeah, I'm not sure that's actually the name for that. There was some debate with Don about this name, Shintani zeta value.
There's definitely something that people call Shintani zeta function.
Yeah, but I think it's a bit more general than...
No, it's more general.
Yeah,
but
this is some special case, yeah. Yeah, absolutely. But in the beginning, people didn't quite realize you just want to study these things, so they were looking at this kind of more general things. But for today, we can just restrict to this. And also to study the relations among these kind of objects, it's you will have to think of cones. That's why I presented multiple zeta values in that way. So I think it's still nice to keep the name. Okay, so how? So let me tell you something more about this series. So you can actually restrict to the case where the determinant of the matrix is 1. So the columns generate z to the n. And I'm not going to talk much about this assumption, but probably later on I will just assume it without saying it explicitly at some point. And you can consider the open cone, which is generated by the columns of the matrix A. And the first observation is that you can write this sum, which was a sum over the trivial cone, if you want, and a sum over this non-trivial cone, but then you take the identity matrix. So you have a simple summand and a complicated summation domain, which is the same thing you have for multiple zeta values, but is now generalized. But this assumption is crucial for this, otherwise you would have some congruence condition in this summation. So this is the first remark. So still, it's a sum over a cone, if you want. So it's a conical sum, at least in this case. And then you also have two integral representations, like in the multiple zeta value case. And to look for these representations, I first introduced the closed cone associated to the matrix, or rather to the transpose matrix. So this is the cone generated by the rows of the matrix A, and I want a closed cone. And then you can prove that you have this integral representation of your conical sum. Of course, here I'm not telling you what is PAK, so I'm not really telling you what's the integral representation, but it's some simple polynomial which depends on A and K. And as in the multiple zeta value case, you have a part of this integrand, the important part, which is canonical, and the complicated part is in the integration, which depends on the cone, and in this polynomial here. And you can do a change of variables, which generalizes the one for multiple zeta values, to take the complicated part into the integrand. So the integrand now depends on the matrix A, but then Q doesn't depend anymore on the matrix A, just on K, and the integration domain becomes very simple. So again, you have these two viewpoints also in the integral representation. Okay, and as in the case of multiple zeta values, now you have two different families of relations which are related to these two different viewpoints on the numbers. So there is the open cone subdivision. Well, first of all, it's immediate to see that product of conical sum are again a conical sum. So you want to look for relations in this algebra. And here is an example. So you have this matrix 1, 0, and 1, which can be written as a sum over the cone generated by these two column vectors. So when I write over n, I mean the cone generated by these two intersected with n. And it's just equal to this. So this is one generator, 1n, and the other one is 0, 1. Sorry, this arrow looks like it's going up to n. This is not a great picture. But anyway, so the cone is just... Yeah, exactly, different scale. But the cone is just something that looks a little bit like this, and then you want to take the lattice points inside of the cone and sum over them. And then you can just split this cone into just going from 1 to n plus 1, and then 0, 1, which is this one, and this one, and then you also have the lattice points which lie on this line. Exactly the same you do with multiple zeta values. And okay, you get this exotic relation among conical sums, which can be rewritten in this way by change of variables. And well, it is what it is. It's a relation among conical sums. It tells you something which is not completely trivial, thanks to these kind of decompositions. Also, notice that this is a linear relation between conical sums. This is one family of relations. And they were first introduced by Guo, Paisha, and Zhang, who studied relations between conical sums, or conical zeta values. Then there is another family of relations which come from closed cone subdivision. So closed cones appear as integration domains in the integral representation. So you now want to play the same game for the integral, but then you decompose closed cones. You don't have to add the measure zero line points anymore. And well, I'm skipping things here, but what you get is, by decomposing this, is some linear combination of other conical sums, where the coefficients lambda I are just rational coefficients, and the weight, as in the open subdivision case, is preserved. At least if the matrix is full rank with the assumptions that I put here.
Why is it rational and not integer?
I guess, let me think.
And previously it was integers, just previously.
I think they may be rational because these numbers come from the Jacobian sum. Let me think.
Well, actually, I guess even in the previous example, you had 1 over n plus 1 squared.
No,
I'm saying
they're rational. They're rational.
You had 1 over n plus 1 squared in the previous example.
Yeah, they're rational. You can think of these as partial fraction decompositions, and you're going to get rational coefficients.
In that example, right?
As I said, you can think of this as partial fraction decomposition of the summand in the series representation. This was already noticed by Guo, Paishan, and Zhang. So I don't think they wrote down this integral representation, but they certainly had this in mind when they studied the partial fraction in the summand, because they called it a closed cone subdivision. And this is completely this is completely the same that happens with multiple zeta values. It's just everything generalizes if you look at things in this way. So you have closed cone subdivision, which reduce to shuffle for multiple zeta values, and they correspond to partial fractioning of the summand in this trivial cone series representation. And open cone subdivision reduced to Staffel for multiple zeta values and correspond to partial fraction for the integrand in the trivial cone integral representation. So I'm not going to comment more on this, but it's just everything completely generalizes. And there is a conjecture by Guo, Paishan, and Zhang that all linear relations among conical sums come from this kind of closed or open subdivision relations, but except that you have to extend them in similar way you do with multiple zeta values by considering divergent objects. And in particular, it means that you conjecture to have some weight gradient, like in the multiple zeta value case. Those all relations preserve the weight. If you don't put this condition on the matrix, so if you consider matrices which are rectangular, so which have more, what I want to say is more columns than rows, like a 3x2 matrix or a 2x1 matrix, then you would have the sum of 1 over x plus y to the k, and there the weight is not preserved. There is going to be some weight mixing, so you need the assumption on the matrix. Okay, so let me give just a little example before I tell you what are the conjectures and theorems on these objects. So this example was the first example that I found coming from string theory, which didn't look completely obvious to me that it was a multiple zeta value. So I was sharing my office with another PhD student, Danilo Lachenko, and he recognized immediately how to reduce it as a multiple zeta value, and this was the starting point of some of this investigation for me. So it's just you have to rewrite this series in this way, and you do some manipulations. It's something quite elementary, but still you would have to think a little bit of how to reduce this to some multiple zeta values. So here there are dots. I'm not going to tell you the answer. You can do this as an exercise, and it's going to be equal to zeta 4 over 2 after all. So first of all, is it clear how to associate this sum to the matrix? So this first form comes from the first row, 1, 0, 1, x1 plus x3. The second row gives you the second form, and the third row gives you the third one. And the third one is wrong.
Why did you swap 2 and 1?
Yeah, that's what he said.
It's just a typo.
Well, it doesn't matter because it's symmetric.
Yeah.
In the 3 variables.
Absolutely.
the matrix. Oh, no, the matrix isn't symmetric, sorry. There's no zero.
No, but I mean, if you
But you can
swap
swap-
x1 and x3,
You can swap the variables,
you would,
and the sum is going to be the
First
same.
and last year.
yes. So it's not
So what I didn't tell you is that there's the conjecture of Gopal-Zhang is I'm being very sloppy when stating it. There are many trivial relations coming from the definition that I've given, because you can do all kinds of like permutation of the linear forms. So you can swap rows and columns of the matrix and you get a lot of relations. The conjecture is after you do all these things, then the only relations that you get are those ones. Okay, so another example. This was the example in the first slide. So you have, no, sorry, it's not this. Yeah, it's the example in the first slide. So here you have some 2 over here. So it's not clear that you should get something which is a multiple zeta value, but you are lucky, and it is. But as I said, you're lucky because in general, you take you put the power of 2 in this factor instead of this one, and you immediately get a log 2. And this is conjecturally not a multiple zeta value. So let me drop the conjectural part from now on about these rings. Yeah, because log 2 can be written in this way, so it's a 2 cyclotomic MZB, so it's with the second root of unity. Good, but you can see the weight here is preserved, and it is coherent with what we expect. And by the way, all this can be proven by this kind of open and closed cone subdivision explicitly. Okay, so I think it's enough for examples and setting. We can go back to zeta values of root systems. Now, what is known about these zeta values of root systems? First of all, let me introduce some notation. Zn is going to be the algebra generated by n cyclotomic MZBs. So Z1 is equal to the algebra of multiple zeta values. Now, the B2 zeta value, which corresponds to SO5, can be proven to belong to Z2. This was proven by Zhao. And the G2 zeta value for the exceptional algebra G2 is, what is this kind of sum? And it was proven by Zhao that this should belong to zeta 12. But he also raised the question, is it in zeta 6? It wasn't clear to him. And as far as I know, it's an open question. Well, we can prove now it's zeta 6, but it was still an open question. And then some general root system, AN, which corresponds to SLN plus 1. This is just what it is. It's some matrix with just zeros and ones. And since these correspond to the rows of the matrix, it means that the ones are always consecutive in the rows of the matrix. And it can be proven immediately just by looking at, well, maybe the n equal 3 case is not so immediate, but n equal 1 and n equal 2 are very easy. N equal 3 is also quite easy. I think n equal 4 is also doable by hands, but it's not, I think, in the literature. But there is the conjecture that these guys should all be multiple zeta values for all n. And it's not a completely trivial conjecture, because if you have a matrix with just zeros and ones, it's not, in general, going to give you a multiple zeta value.
But they only conjecture for AN or for all of the root systems?
No, so I'm not talking about the other root systems. I'm just focusing on this.
But they did. They did B2 and
Yeah.
B2 is a conjecture in general.
I don't think there is a general conjecture on Bn, Cn, Dn.
Yeah,
They just looked at special cases, I think, for the other root systems.
No, you can make the conjecture.
We can make a conjecture.
No, but I'm asking, is this the counterexample? Is it a possible conjecture that they're always in C?
Oh yeah, here it is already wrong, right? Or what do you mean?
Oh, sorry, I meant in Z cyclotomic. Or that you're not.
They're all in Z cyclotomic, and I'll show you why. They're all in Z cyclotomic because of this theorem of Terasoma, who was probably the first who considered this general family of conical zeta values, sums. So he proved that any conical sum is linear combination with coefficients which are roots of unity of cyclotomic multiple values. That's an important result. It tells you that this space is not so big after all. You're still in the setting of mixed state motives.
But then I can ask my question again, because where you join roots of unity. If you do complex sums the way I say, you just sum over the code with congruence conditions.
Yeah.
Is it now a Q-linear combination?
Yeah, so that's a very good point. I believe it is, but it's certainly not proven. It's certainly not proven, and also Terasoma considers something slightly more general. So you put roots of unity also in the conical sums, and of course then you need the QAB part. But his method, I don't think it gives.
No, but one can check on the computer. I mean, is it even conjecture?
So it's I believe for the experiments we have done, I believe you're right. It can be Q, yeah, we didn't do this systematically enough to tell you for sure.
Can I have a question?
Yeah, absolutely.
So for the numerical, so how far do you have like good estimates? How far you have to compute the sum to make it sufficiently different from another one? If you want to just extrapolate like linear combinations in different ways and so on. Like how quickly these sums converge essentially?
Oh, they're very slowly convergent if you do them naively, and it's not easy to find a way to have good numerical approximations. So
you try to integrate this?
Yeah, that's yeah. So there are methods you can try. I think it depends a little bit on the family of conicals.
For usual MCVs, they're very fast.
For usual MCVs and the usual algorithms for MCVs, well, at least the ones that I know, I've generalized them for some families of conical sums, and they get very fast convergence. But for others, I didn't look into this very carefully. But
there is a different way to compute multiple zeta values due to Crandall, and it actually uses this fast representation that you've written, and I assume it can be generalized to these conical sums.
Okay, I'll take a look into that.
Is this using some functional equation to?
No, it uses some truncations of the integrals in the right places.
Thank you. Yeah, that would be helpful to investigate these kind of questions. Thank you. So one thing you can do, so one question is, okay, there are cyclotomic MCVs, but can you predict which kind of root of unity you need? Is there some bound, some effective bound on the root of unity if you are given a conical sum? And it's not possible to extract such a bound from the theorem of Terasoma. One thing you can say, which is a consequence of the PhD thesis of Francis Brown, well, one thing I haven't told you is that this integral representation can be transformed by a change of variables to integral representations which make immediately clear that they are periods. And it's also not very hard, I guess, to prove that they're periods of mixed state motives. And so they fall into the realm of the objects that were studied by Francis in his thesis. And there is one result that can be used to prove that if you can put your matrix in such a way that the ones are consecutive in the columns, like this one, there are no zeros in between any string of ones, then you're going to land on the space of multiple zeta values.
There is a zero. You mean
in the columns?
In the columns. So this is, yeah, exactly. But you could put the zero here and see the same thing happening in the rows because you're allowed to switch columns or rows to obtain this property. Okay, so that's one thing we know. I used this result in my thesis for this string theory kind of sums. And then there was a question / conjecture by Clément Dupont. So he noticed that it seems like if you take the non-zero minors of the matrix A, so all dimension, like 1 by 1, 2 by 2, 3 by 3 submatrices, and you compute the determinants, you take all the ones that are non-zero. You take the LCM of all those in absolute value, then this number should be a period, or rather, is it a period of mixed state motives with Z ramified 1 over n and nth root of unity. So this comes from looking at configuration of hyperplanes in the integral representation of the conical sums. And well, this is a pretty nice conjecture because you can just look at the matrix A and on the spot say which kind of roots of unity you get. And you can immediately refine this conjecture actually because you don't need to take the determinant into this, because by partial fraction decomposition you can just get rid of the determinant of the matrix and reduce as a linear combination of matrices whose LCM is just a proper minus. And an even stronger thing would be if the question raised by Eric is has a positive answer. So Eric noticed that using these kind of techniques of Francis Brown, it seems like you could expect that zeta of AK is in Zn, which is stronger than saying this, because this is known to coincide with this only if n equal 1, 2, 3, 4, 6, and 8, I think. But in general, it's expected to be strictly bigger than this. So this is always containing this. But I think, yeah. Okay. So this would be a stronger conjecture. And this is the kind of question that we were trying to answer with Eric. So I'm going to report now on this work in progress. Some of the things I'm telling you I will already comfortably present them as theorems. So I will have also one claim for which the proof is not completely written down in all details. And
it seems very strange that you need the LCM of the minors like this. So for instance, if I take a 2 by 2 matrix of determinant 1, you already know that the n should be 1, or not. If it's unimodular or not.
Oh, no, it's not.
Oh, no, it's really the LCM.
You have entries which are different from 1 in general, and you will really need higher roots of unity problems.
So if I take A, B, C, D, you really want the LCM of those 4 numbers?
Yeah. Well, in fact, you can get you can do better than that, as I will show you. But so this conjecture is not optimal, at least in 2 by 2 case, but it's a very good approximation probably of what could be optimal, as we have noticed from examples, experiments.
So it implies that if you consider such type of 0-1 matrices, that all their minus would be 0 or plus minus 1.
Yeah, exactly.
But
so
is it obvious?
Well, if you have consecutive ones, it's obvious that it's totally unimodular, which means all the minors are zeros and 1. Well, it's not completely obvious, but it's easy to prove. So in particular, this would hold also for the rows, consecutive ones in the rows for which this is not known. And this would be the case of this AN root system zeta values. So this would set that conjecture.
So why do the minors play a role? I mean, is it a guess? Where is this coming from?
I think originally what Clément did was, so you have these hyperplanes and you take resultants, and you are going to land on conditions which involve determinants of submatrices. So you will have these numbers will appear in the exponents of this. Sorry, they're not hyperplanes, they're hypersurfaces. And then you're going to, yeah, I think that's a good question for Clément, but I'm not sure how we solve this. But if you just run the algorithm of Francis on the easy cases, then from this it's kind of clear, and that's what Eric noticed, that you're going to get determinants. So I would give an example if I have more time of this. It's quite nice how they turn out. Yeah, I think the original computation of Clément, I'm not quite sure how he did it. Okay, so the first result is the following. So you look at 2 by 2 matrices, and you can really do things completely explicitly. So this is, if you want, it's quite elementary. And you can do better than Dupont's conjecture because you have that all conical sums are explicit Q-linear combinations, so you just need Q here, as you asked, of either LCM of AB, cyclotomic M series, or LCM CD, cyclotomic M series. So you don't need the LCM of A, B, C. And an example is this explicit formula for this kind of 2x2 matrices. So here, this is what I mean by explicit. You have this kind of formulas. They're going to be more complicated in the general case, so I'm not showing in the slides. So in particular, so this is proven by essentially using this kind of home decompositions and some
kind of distribution.
Looks more like distribution.
Distribution relation.
Yeah, plus this kind of distribution relation, exactly. And the corollary is that the zeta values associated to the root system G2 actually belong to zeta 6 and not to zeta 12.
So in the theorem, the LCM of A and C doesn't matter.
The LCM of A and C doesn't matter.
It's on the intersection or the union. That's the question.
So you'll have two different parts of the sum. One where you have this kind of LCM and one where you have this kind of LCM.
So it's rank 2, but
They don't mix.
The determinant is 1. The determinant is also 1.
Yes, the determinant is 1. I mean, you can always reduce those who don't have determinant 1s to linear combinations of determinant 1.
I mean, if you state the determinant is 1, then you don't need to say rank 2.
Yeah, sorry.
Yeah, but here the
I guess here this is true also for determinant 1.
Yeah, but the example
Yeah,
is not 1.
It's not 1. Yeah.
C2
Sorry,
is
this is true. This is true also for determinant 1. Yes.
1.
And the example is not a determinant 1.
Yeah,
it's
exactly.
determinant D.
Thank you. And the so what I'm going to call a claim because it's not. I guess it's a tiny example. But this is the last slide. So we still have some details in the proof to fix, but this would settle the question of everybody. So if A is totally unimodular, which means that all the minors are either zeros or plus or minus 1, which means that the LCM of all the minors is 1, then these numbers are multipositive values. So this is a quite strong result on 0-1 matrices, because it's a much more general kind of matrices than the ones with just the consecutive ones in the columns. And so in particular, as I mentioned before, this implies this conjecture of Jean and Joe, because these guys have consecutive ones in the row, so they are totally unimodular. But it tells something quite strong, so it can be used, for instance, in these computations of Zolich, hopefully, if his conjecture is that these 0-1 matrices will give you multipositive values, all he needs to do then is to try to reduce to the totally unimodular case. And just to give you an example, already in 4x4, if you don't have total unimodularity for 0-1 matrices, then you already fail. Because this submatrix in red has determinant 2. And indeed, you get a log 2. You compute this conical sum. So it's maybe not the strongest possible result.
So let's say, and this matrix has what property?
So this matrix is not totally unimodular because the 3x3 has determinant 2. The one with the red numbers has determinant 2. Or minus 2.
Oh, I see. So this is still the case of Dupont's conjecture.
This is still coherent with Dupont's conjecture, but it was also to show that this conjecture is, that this result is quite strong because you already get something. You get already some problems from some very easy. This is actually the simplest example you can cook up with some minor which is not 0, 1, and the matrix is only made by zeros and ones. Okay, so I'm gonna stop here.